factor authors, including Claudia Miller, who's going to speak later today. There is a local cohomology by Brodmann Sharp. And then there are some online notes that you can, if you Google local cohomology Bell Hochster, then you're going to find his notes. And all of these are very good reference for that. But again, you don't have to be an expert on local cohomology, you just need to know, for instance, you know what a Cohen-Macaulay ring is. You need to know that you can know what that means with local cohomology. And things like that. It's not that you have to know, become an expert in 40 minutes. No? Local cohomology. It's just know like this kind of measure this thing, and it says all kind of these things about the ring, things like that.
What's the name of the second?
Brodmann Sharp. This is like, I always mess up names unless I use initial. And I'm being recorded. So it's going to say it's Brodmann Sharp. Yeah. Okay. If you Google local cohomology book, and it's pretty much the only one of the two options that I'm going to do. Okay, so let me start with our condition. Okay, so the sequence of elements in R. Then the check complex associated to this sequence that I'm gonna, the sequence is given by, so we take 0 and then R, and then we take the sum of all the localizations and any of these elements, and then we go to the localization of the product of two elements, and then we continue until we get the localization at all. Okay? Where every map is, so every map goes from one summand to another summand. And from here to here is a localization, no? It's going to be a localization map with a plus or a minus. From here to here is a localization, no? So this is I and J. It's just a localization. So that localization will have a plus or minus. And these plus or minus are not random. Right? It's just those plus or minus that usually every complex works, not like the Cosur complex, the complex that you use for local, for like the original shell complex in differential geometry or the round complexes. There's just plus or minuses. Let me give you a specific example. L is equal to 1. The check complex is this one. That here is just the localization, no, that's the only option, and we'll put it with a plus. So this is the localization. So let's see what is the first. What is the first local? Sorry, the first cohomology group of this complex. Let me just write this. F1 0. What is it? What is the kernel of the localization map? And we know that that is all the elements that are killed by a power of F1. Yes.
For clarity, is R or is 0 the first or 0?
This is the local cohomology group, cohomology category 1.
That's 1. 0 is 0.
Yeah, 1. It's cohomology.
Okay, the R is 0.
Yeah.
0, 1. So this one is going to be the kernel localization map, which is all the elements that kill by a power of a maximum, of the polynomial, so the element F1. So this is union, this is all the elements in R, so that's the exists name with F1 to the n, we do this. And then H1 1, 5 is gonna be, well, that's pretty easy. And again, I know this is not necessarily contained here, but this is like how people write, without the revision notation. This is not necessarily a subset because this is not necessarily injected. Let's do L equals 2. So, let's see what's the map. So this one sends R to localization in never so much, so this means it's sent to R or 1. Just doing different localization. And then we have another one here. This is like something like A, F1 to the alpha 1, and F1, and then A2, or F2, or alpha 2. And then we take the image of this one on the every localization map from here to here. And then the subtraction. And we can see that it's a complex because if we compose these two, we're going to get 0. Is this making sense? Yes.
How do you find the sign in each case?
It is a traditional way. Let me do it. Well, I'm just going to do it now. So for those, if you're familiar with tensor of complexes, is how you assign signs that way. For instance, so let me just write the comments. If you're not familiar with this, I'm gonna give some explanation. No. So the check complex of these ones is equal to how you assign the terms of product from I equals 1 well, for this. You take the complex for this one, and then how you assign to this one is the same as we do to the complex. Let me do it in this case for 2, which makes this thing more explicit. So for 2, how we do the tensor complex? So we have 0, array 1, 0, tensor, 0, array 2, 0. So now we have homological multi. So let me do the 0, 0. The 0, 0 is going to be R tensor R. 0, 1 is R tensor R1. And then the other one is going to be R2 tensor R. Now R1 tensor R2. And then we have this max, this double complex, and then from here to here, we know everything that's zeros, like here we have like 0, 0, 0, a bunch of zeros everywhere else. From here to here, this is like the identity in R, and so the localization map. Localization at 1. From here to here is going to be the localization at, no. Oh, sorry. Sorry. Yeah. We're good? Yeah. We're good now. So, from here to here, this is going to be localization at F1, and so the identity. From here to here is the identity, no, localization at F1, tensor, F2, the local identity in R F2, and then from here to here is, I don't know this right at the first try. So this is the identity in R F1, tensor, localization in F2. Okay? This diagram commutes. So with this we're going to build one complex, the total complex of this double complex. So the same as we do with polynomials, we get the degree for adding the multiple degrees. The degree 0 is this one. Let me just get, I'm just going to write R, because we know this is the same. This one is going to be R localized at F2, and this is R localized at F1. Extensively without doesn't do anything. So R1, F1, plus R2. And then the combinator degree 2 is going to be this one, and then we know that this is just localization as the product. Huh? Okay. So now we have to assign, we know that the maps are localization. If we put these maps from here to these two, once we apply these two, we're not going to get 0. So here's where we know how to put the sign. We're going to make it anti-commutative. We're going to see that going this way is the negative that's going this way. So the way I'm going to do that is I'm going to fix the rows as positive always. Or like what we have in the rows stays. And what we're going to do is with the columns, I'm going to be alternating signs. So plus, minus, if we have something bigger, it will be plus, minus, plus, minus, plus, minus. And we're making it anti-commutative. So let me pick. Sorry. I'm going to do the opposite. I'm going to keep all the arrows, all the vertical positive, and I'm going to be alternating all the horizontals. So this is going to be plus, minus. I mean, it's the same idea. Whatever you assign is going to be isomorphic to this, but I want to be consistent to what I wrote over there. So this is plus, and this is going to be a minus. So from here to here, and we say that all the verticals are positive. So from here to here, both of them positive. So it's the localization map, which is the positive. So this is what we have over there. Sorry, Jonathan, I'm making you for extra. Here. But now, if we do, sorry, it's going to be a lot. I'm going to go in the camera. And then from here to here, we put, we have these ones. And then from here to here, one goes with negative, other goes with positive. And I didn't make a mistake. So the one that has negative is the one in negative. Okay. If you have experience working with the Koszul complex, this is pretty much what happens. The Koszul complex is you take with what element and what you have. The Koszul complex is built also for testing Koszul complexes of only one element. And how you set signs is the same. So if you know how to assign signs with Koszul complex, you will know how to do it with local homology. In fact, something that I'm not going to prove is that you can see the check complex as a limit of Koszul complexes when you are increasing somehow the powers. So that happens. Okay. And it kind of makes sense, no? Because the Koszul complex is the kernel in the first part is like an annulator, and this is like unions of annulators. Now this is the annulator when you are moving the end. 0, 1, 2, okay. Initial. Then I can now B and there generated by the sequence F. And M, B, and R model. Then the ith local homology of M will support. And M is HI, N. So what we're going to do is we're going to take the check complex, which we now know that this is a complex. When we take a complex and we tensor with something, this is still a complex. So we're going to tensor this complex with M. Let me do that tensoring with this. What happens if we tensor this complex with M? What's happening is R tensor M becomes M, RF tensor M is just localization. So it's what we have, but instead of having R's, we put M's.
What's part of on I?
Pardon me? Here?
No, in the what you were.
Oh, it's a product 9, of course. Thank you, Mark. Okay? And then we have cohomology groups of this complex. So, a first complaint that you can do, and it's perfectly valid, is, well, you're telling me this depends on the ideal, but you're defining in terms of the generators. So this is local cohomology does not depend on the choice of the generator. In fact, it's even stronger. Local cohomology does not depend on the ideal, it depends only on its radical. So you take two ideals that have the same radical, then will give you the same local cohomology. These two facts must say that local cohomology is something topological in a sense, no? This is telling us that it depends more on the variety that the ideal defines, in this case plus set. And this one is very similar to, if you have worked with the Check complex in differential geometry, what we do, how we do that? You take like some cover and then assign like some maps in the cover and then play some game there, no? Well, picking set of generators is like picking a cover. And this is like the functions. This is somehow like the functions that appear in the open set given by the complement of the variety given by F1, no? So this is like the functions in the set where F1 does not vanish. And then this one. And then this is like the intersection of those two sets. When neither F1 and F2 vanish. And you can see that this is somehow like a open cover of the complement of the variety defined by the ideal. So the same way, so the proof of this one is very similar, well, in the spirit, not verbatim, of how we prove this for in differential geometry. You get familiar with that. Okay. So, you have seen the Koszul complex. One of the key features is that the Koszul complex can detect depth. No? And how we detect depth from the Koszul complex is by the first non-vanishing cohomological group. No? As I mentioned, local cohomology is, or the Check complex is a limit of the Koszul complex. So local cohomology is a limit of Koszul cohomology. So it measures the same thing, it detects the same thing, and more, in my opinion. So depth of this one in the ideal I is equal to the minimum I, side n, such that this does not vanish. And of course, I am assuming that m is not 0. For this. So local cohomology detects depth, which is now not a topological or geometric property, it's a algebraic property. And I'm not going to say much more, but with local cohomology we have like things like, like Mayer vectores you have in topology, we have like version of Mayer vectores, and for this reason you can use local cohomology to detect whether the spectrum of a ring is connected or disconnected, or how connected it is. There are many things that you can say. It's related to the RAM cohomology, it's related to many stuff. But today I want to focus mostly on algebraic properties and singularity properties. So, well, now we're with that, let me mention a theorem, which is pretty much a corollary of this, is prime K is a local ring, then R is Cohen-Macaulay. Well, by definition, from this Cohen-Macaulay, if and only if the depth is equal to the dimension. No? But we know what's depth, no? Depth is the first non-vanishing. So we're saying that then where this Cohen-Macaulay, if and only if the first non-vanishing is dotted, no? maximal ideal of R is equal to 0 for every I smaller greater than the dimension. But then we can complain, Luis, what if the dimension is also 0? That could happen, no? There's nothing that's preventing us. So here is where a theorem by Grothendieck is what's called the non-vanishing theorem of local cohomology is in a local setting. So local ring. And let T be equal to the dimension of the model. Then HT of M is different to 0. So this makes sense. We know that at the dimension of the ring, this is not going to be 0. Cannot be 0. Okay. Now that we're with Grothendieck, let me just mention his vanishing theorem. So, again, suppose that, no, this is not local. So, let T equals the dimension of M. Remember, M is an R model. Okay, and then suppose that, well, let me just say that, there's assuming M is an, oh, it doesn't matter. Okay, then, HI at any ideal, no matter what it is equal to 0 for every I bigger than. So local cohomology vanishes after the dimension. But remember, how we define the local cohomology is in terms of the shape complex. The shape complex is as long as the number of generators of the ideal. Okay? So we know that the local cohomology has to vanish after that number of generators. Okay? So, sometimes we can use local cohomology to see how many generators an ideal has. For instance, if the 3 local cohomology is not 0, we know that this ideal has at least 3 generators. Making sense? Mm-hmm. So, so we can use that. So here is an exercise. Show that you take a matrix, let's say A, B, C, D, E, F. This is for ideal, sorry, ring. Take the ideal of the 2 by 2 minus of this matrix, and you call this X. Okay, so A times E minus B times D, and so on. This has 3 minus. Show, and then you can prove that the dimension, the height of this ideal is equal to 2. So we know that this ideal cannot be generated by less than 2 elements. But we have 3 generators. Exercise. Show that this one is generated by 3. It cannot be generated by 2. And the question, I just gonna go there. I'm not telling you the answer. Well, I tell you that show question. I'm not going to tell you the answer. This question is are there R1? No, I don't want to get R1 and R2 in a preliminary, so that radical of R1, R2 is equal to 1. Which, you know, it relates to local cohomology. So this is going to be a hard problem, but it's going to be a lot of fun. Okay. So now let's do some graded version of local topology. Okay, so let's do some specific settings. So again, fake is a field. Because we're going to relate this with Frobenius, just assuming that this is a finite field. Or you may assume one that K is perfect. Or if you want, you can assume that K is algebraic. Any of these is fine. Okay, and then suppose that R is a finally generated K algebra. This is just a project. No. Yeah, as a standard graded finally generated K algebra, this is just a fancy way to say take a polynomial ring. Some variables. Every variable has degree 1. And then take a quotient over some ideal that is homogeneous. Are we good so far? And in our setting, we're going to take n that are generated by the maximal, the variables, or the class of the variables, which we're going to write the same as the variables. This is the maximum homogeneous ideal. Okay, so duration, if a sequence of polynomials now, if this polynomial is graded, is homogeneous, is a sequence of homogeneous polynomials, then every localization of a homogeneous polynomial is an homogeneous ring, no? So then the check complex is a graded complex. Because localizations, as we say, are graded, but also the localization map are homogeneous map, no? Homogeneous at degree 0. So, if M is a graded R model, then the local homology of any ideal which is homogeneous, for which we can pick a set of homogeneous generators, this one is graded, or segregated. M is graded model, finally generated, then its local homology at the maximum homogeneous ideal is an Artinian model. So it satisfies the descending chain condition. We're going to use only the graded version, but I mean, there is a local version of this one. If R is local ring, N is a finally iterated model, then the local homology, any local homology at the maximal ideal is also Artinian. I want to focus in the graded case for the following cool fact. So let's continue with N graded. So let's follow the idea scheme. Let's take N, sub N equals to take the local homology at the maximal ideal for some I fix. And then these are going to be at that ideal was degree is at most n. No, sorry, 35. Bigger or equal to n. Bigger or equal to n. So, what's there? Let's see n natural number. So, first we want to take the part of positive degree. Because multiplication by elements in the range does not decrease the degree, only can increase the degree. So this is well-defined R model now. And then when they want to degree of this one and this two and so on. So we have that this one is a descending chain of models, R models, graded R models. So this has to stop. So there exists, since H-I-M is here, there exists a theta such that n is equal to n theta for every n greater or equal to theta. But what is this telling us? Let's just look what happens at n theta plus 1. So, n theta plus 1 is equal to n theta. Just what the consequence. So this implies that n theta plus 1 over n theta is equal to 0. Nothing fancy. But what is this if we look at the definition? This corresponds to the part of degree exactly theta, no? Because we kill by assumption anything that is smaller than theta, and by taking, by taking this quotient, we kill anything that has degree bigger than theta. So this corresponds to H-I-M-M of degree exactly theta. So that has to die. And then we can continue doing this for anything that goes above, and everything of degree bigger or equal than theta has to vanish. So local cohomology has a top degree, because starting some point, it becomes 0. If the model is not 0 now. So this top degree has the following name. That's called the A invariant of the model. Some definition. Let n be a graded model. So, if the local cohomology at the maximal ideal, the following setting, is different than 0, the A invariant of M is the top local degree, is the maximum n, such that the I local cohomology of M with support of the maximal ideal is different than 0. And this is well defined from the observation that we did. If this local cohomology does vanish, so we said the invariant is going to be minus infinity by convention.
Equal to 0.
Yeah.
Equal to 0.
Oh, of course, thank you. Sorry. I'm using more coffee, so don't forget. Okay, Yeah.
Sorry. Is there any sort of nice behavior for the A invariance as we vary I?
Not that I can think of. I mean, the I has a nice behavior and it says nice things. We're going to see that in a moment, but as long as we vary I, no. That I can think of right now. Well, we're about to see some cool stuff about this. So, this is going to be my official definition for the Castello regularity. So, given a graded model, and it's Castello model regularity is defined by. So it's going to write as regularity of n, and this is equal to the maximum. The I. So the invariance, a lot of times you're going to forget of the n there, if it's clear from the context. I hope that's okay. Plus I. So an I moves where the possible non-vanishing are 0 until the dimension of n now. Because outside this range, it certainly becomes 0. It may become 0 in this range, but you get a bunch of minus infinities. But we know that at least one of them, we know that at least one of the local cohomology models does not vanish. So we're going to have something positive here. Well, no, not positive. Something that's non-negative infinity. Okay? So this is well defined. Some cool theorem about this is, in this context, if n has a minimal set of generators, set of homogeneous generators, V1 until V sub L, then the regularity, as we define it, is bigger or equal than the degree of these generators. And this is not surprising if you have seen other definitions of Castello-Bowman regularity. So let me just give you just a review of free resolutions, but you're going to see a lot more later today with Claudia. So let me just recall. I wanted to recall from yesterday's lecture, but it didn't happen. So let me just write R equals as S over I, where S is a polynomial ring, and this I is homogeneous. Okay, and then again let M be a graded model. Okay, if M is an R model, by de facto is an S model now. So we can take a free resolution of M as a free model. We take a free resolution, we pick a set of homogeneous generators, and then we pick this one free element, one R for every generator, and then because we want this to be homogeneous of degree 0, we have to twist the degree in R, and then come and twist with it of part J, we call that the B0, J, which is telling us how many minimal generators of degree J we have. And then we have the kernel of this one, the first CC group, the CCGs. So we take the kernel, that has to be homogeneous, and then we apply the same thing to the set of generators now. These are called the graded Betti numbers. And so, theorem. The Casanova move for regularity of M is equal to the max of I minus J minus where beta I J of the model is different of zero.
Sorry, did you want to resolve M as an R module or as an S?
Oh, thank you, Jack. As an model, of course, because I want this to stop. Thank you, Jack. Yeah, as an model. So this is kind of well, first let me mention a few words about this theorem. The first one is that this is proven using this fact. This is part of like the heart of the proof, or one of the key steps. Because this is like somehow saying that the regularity that we define is bigger than any of these. But this any of these, no, J minus I, sorry. Yeah, J minus I. That's the part I also find. Okay, but so, and then this, the max of this J minus J minus 0 has to be here, no? The ones there. And this J corresponds to the degrees of the minimal generators. So saying that to prove that this is bigger than the part given by this one is the same as proving this. Let's just follow some sort of idea. Another thing is that these Betti numbers, as we define them, depend of a presentation, no? How we write R as a quotient of a polynomial ring modular of homogeneous idea. But the way we define regularity using the eigenvariance, we use no presentation. So this is telling us that at least how this varies in the free resolution does not depend on the presentation. And the regularity, which is totally from local homology that we define that way, is telling us somehow the complexity, or part of the complexity that is going on here. Okay? Luis? Yes?
So was the A invariant defined for any graded ring, graded module, or
For any graded model.
or was it just for regular?
No. The invariant, here we didn't assume anything of the ring, it was R.
So then should this, I mean, I'm confused. Should this be R? And should this be regularity over R? And then be
No, because regularity we define the eigenvariance, and the theorem part is that this is equal to the thing done by the Betti numbers, which do depend on the presentation a priori.
So it's the S Betti numbers related to the R regularity?
Yeah, pardon me?
The S Betti numbers are related to the regularity of the R?
Yeah, which does not depend on S. That's part of the theorem. Independence of, because I know that most people, when they give a lecture, they define the Betti numbers this way. The regularity this way. And a priori it seems that it depends on S. But because I defined it differently, regularity by my definition, from the definition that we gave today, does not depend. But they still tell us something about the Betti numbers for any presentation. Okay. Okay. Yeah.
And is separated harmonic,
Yes, this is. Yes.
but the resolution is over S.
Yes, yeah.
Okay.
This is.
Why we use R and S differently?
Because what I want to say at some point, I wanted to recall that the projective dimension over S, here over S, of n is equal to the max I, such that beta I j of n is equal to 0. Because I wanted to define this. In order to define this, I need the resolution to be finite. But because I'm not assuming anything over every model, and I really want this to be, I want this to stop, no? That's why I need regular.
Yes.
Yeah. But this is not for the definition because I wanted to do this. And I wanted to recall the Alexander-Boltzmann theorem that says that, let me just write here, that that the depth of M, so the projective definition, dimension as we did over S of M, is equal to the dimension of S. Okay? So the projective dimension will depend on S on this presentation, but we take that minus the dimension minus that, then does not depend on, because that. Okay, are we good? This finishes the crash course, the tiny course in local homology. Any question, comment?
Not a question, but I feel like since you wrote regularity and projective dimension, in case anyone hasn't seen it, it's really nice to see that you can read them from the Betty table, but by the width and the height of the Betty table.
Yes. You write the better table, then is the number of rows, no?
Yeah, regularity is the number of rows and
Projective dimension, the number of columns. Thank you. Okay.
1 hour.
That's really
Okay, so now let's talk about point characteristics and local communities. Did it fine?
yeah.
I have some question
Yes.
about the local homology. When we compute possible homology, we can build the possible complex from, in the case of ideal, in the case of monocle ideal, from certain simple cell complexes. In this case, can we do something similar?
I think so. I mean, there is a, well, I don't think what you're saying, but I can tell you that when you have like you restrict to centralized rings, or structure monomer, there is a lot of combinatorics and there is a lot of things that you can read. For instance, yeah, there is a lot of things. Okay. So let's go back to prime characteristic. So now we're going to define a bunch of types of singularities using Frobenius, and then we're going to start discussing a lot of things about them. So, definition. So we say that a ring is pure if for every R module M, the map. So we have a map from R to the model of P roots now. We discussed that yesterday. So I'm going to tensor this with respect to M tensor R, M tensor R. And this map is given the identity name, tensor, the inclusion that we discussed. If this map is injected for every element, is what it is injected. Okay. Okay. That is the first type of singularity. The second one, if you say that R is F split, if the inclusion that we have this map splits, so that means that there is a vector, let me write it wrong, such that rho imposed with an inclusion is equal to the identity name. This is equivalent to say that as R modulus, so this map is a map of R modulus. So this says that as an R modulus, R 1 over P is isomorphic to M, to to R plus something else. And this is some sort of retraction. No? You think like in invariant theory, this will be like a ring of invariance and this like the other thing bigger and you have the retraction. No? But this is pretty much the ring, the retraction from something that this is homomorphic to it, but it's also kind of bigger. No? And this is how we play, you know, the fractal that we were talking about yesterday. This is how we're going to do like a lot of games. So a map from here to here will let us like play this game, but there are some maps that are very special, and those are these kind of retractions. So we're going to call splittings. Okay? And the third one is we say that R is F-injective if, before I give you the punchline, I want to do an observation. We have here R localized at F. Just that. F is an element. And I'm going to do it twice. Because R is a range of prime characteristics that we are assuming in this course. There is a frobenius from here to here. But this is a range of prime characteristics, no? This is a frobenius map from here to here. And this commutes, no? This diagram. So if we take the kernel of this map, is going to be stable over the Frobenius. The image of this map is going to be stable on the Frobenius here. So the co-kernel is going to be also stable. We will have a Frobenius action, a Frobenius map there. So this can be extended to any local cohomology. No? This is local cohomology of one element, but we can do it over any local cohomology. Okay? So we say that the local ring, we have a local ring R and K is F-injective if the Frobenius map used on the local cohomology is injective for every element. Now, yesterday we saw that taking Frobenius map is the same as taking inclusion in roots now, which actually I claim that I like more, so let me just switch this. I forget here about Frobenius, here about Frobenius. What I'm going to do, so because Frobenius, this map that we have here, R and R. We have R, we have Frobenius, we have R, and then we saw that this was equivalent to R1 over P, and then here we have the map F tilde, and then here we have the identity map. The diagram we have yesterday. Let's apply local cohomology to this diagram. So being F-injective is going to be equivalent to say that the map of R1 of this time from the local cohomology at R to the local cohomology at R1 over P is injective. Okay. So we have these three definitions. Exercise. any of these properties is satisfied, these properties are equivalent to the respective parts if you put this at P to the E, for one E bigger or equal than 1, or for every E. As we discussed this similar type of flavor or result for a finite, for regular, so the same thing happens here.
This first property means that you're related to R1 over P being flat over R.
No, well, yes, you know what I mean. Because what you're saying is equivalent to be regular. And every regular ring is a pure. We're going to discuss that. In fact, we're going to prove that a pure, F split implies a pure. We're going to show that, well, we're going to see that F split implies F injective pure. And actually, yeah, and we're going to see a bunch of relationships. And we're going to relate that to the regular. Okay? No. Let me just. Okay. Let's do the first relation. Now. First observation. R is a split F split. So what we have? We have that R goes to R1 over P. We have here the inclusion, and then we have the retraction. No? The composition of these two is the identity. Let's apply this Docker homology to this. Because Docker homology, at the end of the day, is a functor. So functors behave nice with composition, no? It's going to send identity to identity and the composition to the composition, no? So the composition of these two, the two maps by Docker homology, has to be the identity.
Does it reverse errors or does it preserve them?
Preserve. Yeah, no, because I mean, you take a map from something, and then you take this map with the check complex, everything stays the same, no?
I didn't expect that.
Yeah, no, okay. Let's click now, or
Exactly.
so, or let me see it different way. So we know that F split says that this element, this ring, is equal to R plus N, or something like that. If we apply local homology, and then we can see that local homology behaves well with direction mass. So this is. So the local homology also splits. And this mark here is the same as the identity if we restrict to this part. Is this one going to the inclusion? So it has to be injected. Oh, what I'm saying local homology. I'm proving that F split is F injective. I want to prove that F split is pure. But anyway, so conclusion. F split implies F injective. Okay? Okay, now let's do the one I wanted to do. I'm sorry. But it's the same, no? It's just taking functors. So R goes to R1 over P. We have the inclusion, we have beta. Now tensor this diagram with any M that you give me. So here we have this M tensor, this one, and M tensor, this one, this map. So this has to be the splitting now, because tensoring maps also behave well with composition, and tensoring with identity gives the identity. Another way to see this one is M tensor R plus N. And we know that tensor product behaves well with directions. So this is R plus M tensor N. So So this map has to be injected because this one, from here to here, corresponds to taking this one and then going to the first entry. So this has to be injected. So, conclusion, F split implies F injected. Sorry. Now, I want to prove, well, quasi-prove, the following theorem, Foster and Roberts. Let's see the following. Let R be an finite domain. And I know that this is, well, I know that all things here are finite. So I'm just like trying to really express that this has to be finite. Let's do remind us of self. Then R is F cubed if and only if R is F split. Okay. So in the case that we're treating in this short course, F split is the same as F pure, so they are synonyms. Okay? So once we prove this, I'm going to use these words as the same. And in fact, my personal preference is to use F pure, even though a lot of times I mean F split, but you know, it is the same. It's okay. Okay, so let me do a lemma, which is going to be an exercise. So what it says is the following. Let this denote the functor come up. Let Ri, let M be a finally generated module with a presentation RA, RB, N. To take a presentation, the map here is going to be phi. We know that this map is given by a matrix. This is map with three models. And let N be equals to the cokernel of phi dual. So we're applying this functor. Now, let A, B, C be a short subsequence of our models. Then the kernel of A tensor N and B tensor N is isomorphic to the kernel from of MB from MC. I'm not going to prove that, but that's like the exercise. Okay, but I'm going to use this. We're going to use this to prove the Foster-Roberts theorem. And you can see what's going to happen, no? Proof of the Foster-Roberts theorem. Okay. So the part I want to prove is that F cube implies F split, no? That's the part I want to do, no? Because the other one we just saw. So, I mean, here's the lemma is kind of screaming at us what to do, no? Here we're going to use a purity, no? We're going to get some kernel equal to 0 because it's going to be no purity. And then the A and the B has to be, let's say, the A has to be R and the B has to be R1 over P, no? The part that we have to do is try to pick what is the N. Well, and we don't have to do what's the N, we have to know what is the N, so we get the N. Okay? And once we get that this is going to be 0, we get a kernel equal to 0. And what's the kernel being 0 telling us here is that this map is rejected. No? So we get some injection translated to some rejection. Okay, so the trick is try to reinterpret or to think of splitting in terms of certain map being rejected. That's the key part that we have to do here. Okay, so so this is, we're going to take R1 over P R. We're going to take a presentation. Okay. A presentation of this, and I'm going to call this P. I'm not saying that this is N, by the way. Let me just start it. Now. FC. Okay, the bottom. Okay? This is, so I'm gonna set, we're gonna set M equals the cokernel of this, of the dual of this one, of FC. But because we're working with free models, the dual corresponds to the transpose, no? Then, what happened with that, we take what is going to be the cokernel of the dual of the dual. The same of the cokernel of the transpose, no? Which is the cokernel of C, which is R1 over P over R. So, the trick here is not go and put this one to be N. We're going to take N to be this thing. So when we take the kernel of the kernel, sorry, the transpose of the transpose, we get the region. That's the trick there. So, I just want to mention, because I don't want people to get the wrong impression, I'm not saying that this functor is a duality. People like to think this is a duality, but this is not exact. And in general, if we to take the star of the star, you don't get the same thing always. Here is something very special because we have a map of free models. Okay, so now we consider the short exact sequence given by 0 R1 over P, R1 over P over R. This is something we knew we have to take in order to do this. But now, this is our N now. So, apply the theorem. So, kernel of A tensor N, B tensor N, which we know it's 0 because our ring is a pure. This is the same as the kernel of R1 over P over R. That's my N, and then my P is R1 over P to from R1 over P R to C, which is the same, R1 over P, R. So this is equal to 0. So this map is surjective. Here we have a very special map, no? The identity. So what we're saying is that there is something, the kernel of this map from here to here is identity. So what's telling us is that it's telling us that there exists a beta inside com R1 over P over R to R1 over P, a map, such that when we go this map, what is this map? Is post-composing, no, pre-composing with the induced map from here to here now. Let me just call this map pi. So what is it then? Such that beta composed with pi is equal to the identity here. So let's break this here. So we have here pi. We know that there exists something that goes here, beta, and when we go, no, this way, yeah. I wrote it wrong, sorry. This is pi composed with beta. When we go this way and then this way, we get the identity. But this is equivalent to this thing splitting on this side. But once we get the splitting on this side, it's splitting the other side. So the trick was focusing in this part to get surjection, to get the splitting in the other side. Okay, so hence, R1 over P is isomorphic to the two sides, which is R plus R1 over P over R. Okay? Okay, so
I have a question. In what part of the proof did we use that R is
in this one, because we're using that M is finally generated model, so we need that this element and its dual are finally generated. We use that this is final. Yeah, that's a good question. Thanks. Okay, so now let's see consequences. Oh no, examples. No? I only do examples. So theorem. This is not this is my feather, and this is called, sorry, usually called a Feder's criterion. And it says the following: let S and K be a regular local ring, I containing night and ideal, and R to be equal to the quotient. Then R is Q if and only if we have these powers forgotten, so let's just recount. You know, the ideal generated by the 3 powers of I. This one is not contained in M bracket P. Again, here we can put P or P to the E for any E bigger or equal than 1 or for absolutely every E positive. Okay? I'm not going to prove this because you're going to prove this, but for this one it's not going to be just an exercise. We're preparing a worksheet, so you work in teams proving this. This is going to be done probably on Thursday. Okay, so it's like this is going to be your job for Thursday. Because today I expect that you finish, do more problems, that you have more time to think about them. It's not just like 5 minutes and then rush to solve something. and we're going to give you some additional problems also today. But this is for Thursday problem session. Okay? It's a worksheet that I hope you collaborate to solve this, and hopefully one day to prove neural theorems and things that start moving faster. Okay. Okay. I should mention that this has a graded version, no? We can think that S is a polynomial ring, M is homogeneous. This is the homogeneous maximal ideal. R is the quotient, so it's a graded K algebra. And then it's a pure if and only if, because this is homogeneous, this column ideal is homogeneous, and then this makes sense, no? So sometimes we're going to use the graded version. Actually, we're going to do it now. Now we're going to talk about examples. So, first example is if R is regular. I mean, somehow that is going to be implicit in this. But one of the problems yesterday, I think the presentation is, no, we saw if R is regular, then it's regular and local, then R1 over P is free, no? So it has to be pure. So that's an example. We don't need Falaise criterion. But let me do something that is a bit standard rated rings. Okay, so what do I mean by that? S is a polynomial ring, it's a very variables. Let me tell x1 and x2t. And I is a square free monomial ideal. So it means that the ideal is a monomial ideal that is radical, no? A radical monomial ideal. So we want to show that the quotient is a pure. So we have to prove this. Okay? So we're going to build an element that is here and that it is not here. So let G be equal to x1, x2 to the p minus 1. Okay? By construction, this element is not in x1 to the p, xt to the p, which is the same as m bracket p, no? Okay? So we got this part. Let's do the other part. If you give me any, let f be any square free monomial. So that means that this exponent is either 0 or 1. Let's assume that it's different one. And okay, so what is G times F is equal to, first let me call this vol 1 to be the exponent 1, 1, 1 here. So T1s in a vector. So we take this product, what's going to happen is, like here, whatever here we have ones, once we multiply by this one, we're going to be adding 1, no? So we're going to get p's. So this is going to be x2 p alpha. And then whatever doesn't have p's, this is the same as, sorry, we're going to get 1 minus alpha. So we have ones in the, where we had zeros before, and that is p minus 1. And this pretty much does not matter, as long as we know that this is a factor. This is going to be inside the ideal generated by x to the alpha bracket p. And this, if x to the alpha was in I, then this has to be contained here. Okay? So, if f is in I, G times F is in A bracket P. And we're going to have this part. So for any monomial ideal, a square-free monomial ideal, we have an element that lives there. And that doesn't live here. So any square-free monomial ideal is F pure. And this is the moment to give an imprecise theorem. And then this or quasi-theorem, if that makes sense. Pure rings are very similar, not the same, as the standard Reisner ring. What do I mean by this? Let me so here what I mean is in two directions. First, if you have a fact about the standard Reisner rings, a fact can be probably or can probably extends to a pure ring. So if you say a theorem about standard Reisner rings, then probably you will see a theorem about the same property about the pure rings in general. And we haven't seen this yet, but there are a lot of the pure rings that are not standard Reisner. So it's a much bigger family. And tomorrow we're going to see this, an example of this in symbolic powers. So that's one direction, that you have standard Reisner, you have pure. And what you see this is like standard Reisner rings are a very representative class of pure rings. But it also goes in the other direction. So a result of pure rings, probably holds for all standard Reisner rings. And you can tell me, hey Luis, I mean, you just told me that a pure ring, standard Reisner rings are an example of pure rings. It's true in prime characteristic. But in characteristic 0, we don't have pure rings because we don't have Frobenius. So if you give me a result of pure rings or of in characteristics P, then the proof sometimes can translate it to a proof of a standard Reisner ring in any characteristic, in some sort of like Frobenius-like morphisms. There is like a game that you can do. And together with Alessandro De Stefani and Jonathan Montaño, we wrote a survey on these kind of problems. It's in the archive. It's called Frobenius in Combinatorics, so that you can see a ton of examples about this in many directions. But I know you have a lot of things to do. We're going to do one example for symbolic powers tomorrow.
Just give me extra rings, right? In the second section.
Oh, yeah, rings now. I'll take it. Okay. You know what? Yeah. You know what to do? Okay. Oh, yeah, I probably should have stopped because we have only 2 minutes. Okay, that's it for tomorrow. We do more examples, and then we see this philosophy in action.